class 12. In the previous class we have learned about that to find the electric potential due to an electric dipole at any arbitrary position at the point P, and from special cases we have learned for axial when theta is equal to 0 degree, for equatorial when theta is equal to 90 degree. We obtain in this way, right? The expression of what electric potential on an axial line will be equal to 1 by 4 pi epsilon naught P by R square, where P is your dipole moment. Okay, and electric potential is a scalar quantity, so no need of having that vector direction onto this dipole moment. And for that of electric potential on an equipotential surface, it was found to be 0. Okay, for today we need to learn about that relation between what electric field intensity and potential. After this, later on we will try to learn about equipotential surface, and at the end we will try to learn about some properties, rather important properties of equipotential surfaces. Okay, so let's try to find out the relation between the electric field intensity and potential. There is a relation between electric potential and the electric field intensity. Now you consider 2 points A and B. Okay, this is one point where a charge is placed at O, and due to this charge we need to find out electric field as well as potential at this point. Okay, now your electric field E, this point A is well within this electric field of this given charge. Okay, and so what happened, we need to find out electric field, the expression between and the relation between electric field E at this point and the amount of work done in bringing that test charge from infinity up to this point. So let's try to find it out in that way, and we will see the relation between this electric field intensity and the electric potential. Okay, so let's consider 2 points A and B, which are very, very small, infinitesimally small, and E is the electric field intensity at that point due to this plus Q. Okay, at O, that means at O Q is residing there, and we need to take it electric field E intensity at a point A. This E is due to this charge plus Q at O. That is the meaning. Okay, now work done to move the test charge from A to B. Okay, from A to B, an infinitesimally small distance dr. The small amount of work done will be denoted by dW, and we know that work done is expressed as force dot displacement. So your force is acting along this direction. We know that electric field is equal to force per unit charge, so your force will be what? Electric field times that charge, right? So your force experience will be Q naught E along this direction, Q naught times E along this direction, right? So what happened, your F is acting along the direction of E vector, and your dr is just opposite, so angle between them will be cosine of 180 degree. So your dW will be equal to Q naught E times dr cosine of 180 degree. So your dW by Q naught, you transfer this Q naught to the right hand side, so that it will be dW by Q naught will be equal to minus E dr. So your dV by dr, this is what actually dV. Okay, that small electric potential difference, right? So small potential difference divided by this dr, small infinitesimal distance, this will be equal to minus E. So therefore your electric field E can be expressed as minus of dV by dr. This dV by dr, we call it as potential gradient. Potential gradient is nothing but the change in the potential with a small change in distance. That small change of electric potential with a small change of distance, we call it that as potential gradient. You might have learned in class 11 also about velocity gradient at a time of what, viscosity, right? So at the time also I have told you that it will be learned again in the case of electrostatics again. So you must be remembering. So what happened, this potential gradient, okay, and this E, they are related as E is equal to, E means electric field intensity, is equal to minus dV by dr. So thus electric field intensity at a point is equal to the negative gradient of the electric potential, or you can say like this, electric field intensity at a point is equal to negative of potential gradient at that point. Got it? So now what happened, we come to know that this electric field E is equal to minus of potential gradient. What does this minus represent? That is the question. Okay, what does this minus sign or negative sign represent? This negative sign represents nothing but your electric field E is in the direction of the decrease in the electric potential. So we know that if your charge, suppose here, so let's take it here, this is a Q charge here. Suppose a Q charge is here residing, okay, we have taken as plus Q. Mouse is not so good. So let's take it that this Q is residing here, and let's take it this as plus. Got it? Plus charge is residing here. And suppose if you want to find out electric field E, then what happened? Electric field E is in this direction, right? Being positive here, your electric field E. What is wrong with this mouse? E will be acting along this, right? And we know that electric potential, further the distance, electric potential will be less. V will be less here, right? Less, let me write with the arrow like this. Less means down, arrow down. So V is less, but somewhere here, what happened? Your V, as you come closer and closer, that test unit positive charge from infinity, if you bring closer and closer to what the given charge, what happened? Your V will be increasing, right? V will be increasing, its value V will be what, more, right? Like this, right? So what happened? So your electric field E is in the direction of decreasing electric potential. So electric potential decreases when you go further and further, then electric potential decreases, right? So what happened? Your electric field E is in the direction of decreasing electric potential. That negative sign indicates or represents that the direction of electric field E will be in the direction of decreasing electric potential. That is note number 1. Note number 2, electric potential, as I have said earlier, that electric potential is a scalar quantity, while electric potential gradient is a vector quantity. Don't forget this, okay? Electric potential is a scalar quantity, no doubt, but your potential gradient is a vector quantity. It has a direction. Got it? So what happened? Because of that only, your E is equal to minus dV by dr. Electric field is also a vector quantity. Your potential gradient is also what? A vector quantity. So your negative sign represents that potential gradient, what? And electric field are opposite. Your electric field is in the direction of what? Decreasing electric potential gradient. Got it? Had there E is equal to plus of dV by dr, then what happened? Your electric field would have been in the direction of that potential gradient. That means increasing potential. Got it? But it is not so. Minus means what? Your electric field E is in the direction of decreasing potential gradient. Okay? Yes. Or what potential gradient and the electric field are just opposite, you can say in that way. Now let's see in the case of what the electric potential, what is meant by equipotential surfaces. Okay, equipotential surfaces are nothing but these are surfaces, okay, which have same potential. So if you want to say in a singular form, an equipotential surface, an equipotential surface is nothing but is a particular surface at every point on which the electric potential will remain same. Equi means equal, so equal potential. So at every point on the surface of that particular surface, at every point onto that surface, okay, electric potential will remain same. Such type of surface is known as equipotential surface. Definition is given here. An equipotential surface is that surface at every point of which, that means at every point onto that surface, your electric potential is same. So in the case of spherical equipotential surface will be from or due to a single point charge. Okay, so if this is a single point charge, then what happens, its equipotential surface will be spherical in shape. Got it? As the distance are same, what happen, your potential due to this charge at this point on its what surface, that will remain same. We can't draw that sphere, so you can imagine that this is a circle, so it will be represented by concentric circles in 2 dimension. Okay, but don't think that this is circle, rather you have to assume that this is what, spheres. Okay, spherical shell, in that way you can take it. So what happened, being onto this surface or at the same radii, what happened, potential will be also same. Okay, so this is one equipotential surface, another equipotential surface, another equipotential surface. Okay, so but these are different equipotential surface. Potential here and potential here will be different. Okay, let me zoom in, okay, so that you can see very easily. Now these are three equipotential surface. One equipotential surface here, another equipotential surface, got it, another equipotential surface. So if you take one equipotential surface here, the electric potential onto these points, okay, will be having the same value. Okay, but equipotential onto this second surface will be also same, but I'm telling you that the equipotential, the potential at one equipotential surface, the potential at another equipotential surface will be different. Potential here and potential somewhere here will be different, but as long as onto that surface, potential will remain same. So this is one equipotential surface, this is another equipotential surface of whose electric potential are different. Got it? Different means onto the different equipotential surface, electric potentials are different. If it is on a single equipotential surface, electric potential are same throughout that equipotential surface. Got it? In the case of what, uniform electric field, your equipotential surface will be plane like this. Got it? So if the electric field is uniform, then what happen, plane equipotential surface will be formed. And I'm telling you that this equipotential surface and the electric field lines will be always perpendicular to each other. Here you can also see that these are the plane equipotential surface. There are 3 equipotential surface. Okay, potential at here and potential at here will be all different, but potential onto this same surface will remain same, as I told you, right? And electric field E, this is the direction of electric field E. Okay, and this is the equipotential surface. So equipotential surface and electric field E are always perpendicular to what, each other. Got it? Yes, this is of a dumbbell shape. Okay, equipotential surface is of a dumbbell shape if the point charges are of similar similar nature, plus plus minus minus, like that. It will be of this shape. Okay, onto this surface, what happen, electric potential due to these two charges will be having the same value on a particular equipotential surface. Got it? In the case of what, similar point charges. But if it is of what, dissimilar in nature, magnitude may be equal, but the nature will be different, just like an electric dipole. Okay, in that case, what happen, equipotential surface will not be in the shape of dumbbell, rather it will be in the shape of like this. Got it? This arrow lines, this represents electric field. Got it? Starting from the positive charge and ending toward the negative charge. Okay, these are the electric field lines. Got it? These are the electric field lines, right? But equipotential surfaces are here. It is just not a spherical in shape, rather it will be in the form of ellipse. Okay, in the form of ellipse in the two-dimensional figure. Okay, it is just like an oval shape, just like the egg shape. Got it? So what happened in between these two, the dissimilarity or difference between these two, that means for a similar point charges and dissimilar point charges, what happened in the case of what this dissimilar point charges, your equipotential surface will be close, very close or crowded in between the two charges. Then somewhere here at the farther point, see, you will see that equipotential surface are becoming closer and closer and closer, right? But somewhere here away from them, these equipotential surface are farther away, right? But in the case of these similar point charges, it is just opposite. Far away it will be becoming somewhat closer, and in between them the distance between the equipotential surface will be farther apart. Okay, the distance of separation will be more when it is away from the charges. And the distance of separation between any two equipotential surface will be very less in between the two charges in the case of dissimilar what electric dipole, just like that of electric dipole. Okay, so this is also one of the, in just in the middle of this electric dipole, what happened, it will be flat and it will be having plain equipotential surface in the case of electric dipole, but others will be curved like this. Got it? Yes, let's see about the properties of equipotential surface in the next. Okay, so here it is what, properties of equipotential surfaces. Number one, no work is done in moving a test charge from one point to the another point on an equipotential surface. On the same equipotential surface, if a charge is going to be taken from one point to another point, then no work is to be done. We can prove it mathematically. Your potential difference VA minus VB, this is the potential difference, right? Potential difference is defined as the amount of work done in bringing a test charge. That work done will be from in bringing from A to B or B to A, doesn't matter. Okay, in taking from A to B or B to A, that is the work done in moving from A to B. Let's take it by a test charge Q naught. So what happened, as these are at the same what equipotential surface, A and B are on the same equipotential surface, the electric potential will remain same, right? So difference of same quantity will give you 0, right? Work done in bringing A and B divided by Q naught. So this Q naught is a non-zero quantity, so if you cross multiply it, then it will be give you 0. So your work done in moving from A to B will be also equal to 0. That is how we prove it. Okay, so no work is done in moving a test charge or any charge from one point to the another point on the same equipotential surface. Number 2, electric field. As I said, your electric field and equipotential surfaces are always perpendicular to one another, right? So that one, it will be also here. The electric field is perpendicular to the element dl of the equipotential surface. This dl is a line drawn on that equipotential surface. Okay, so f dot dl If you want to find out work done, then F dot dl will be the what? Small work done divided by Q naught. You can take it from here. Okay, small work done divided by Q naught will be equal to what? Difference in potential. You can take it from here. Okay, so this potential, as these two are of same potential, because it is on the same equipotential surface, potential at A and potential at B will be same, so difference will be 0. So force per unit charge, it is known as electric field intensity. So electric field intensity dot dl is equal to 0. So this E is a non-zero quantity, this dl is also a non-zero quantity, and if this dot product is going to give, then what happen? The angle between them must be what? 90 degree, otherwise cosine of 90 degree. Okay, if cosine of 90 degree is there, then this will be always equal to 0. So your theta must be what? None other than 90 degree. That means angle between this electric field E and this dl on the surface must be 90 degree. That means they are perpendicular to each other. Okay, that means electric field E is perpendicular to the equipotential surface, right? Next point, equipotential surface indicates regions of strong or weak field. As I told you in that, while drawing that equipotential surface of two like point charges and two unlike point charges like that of an electric dipole, I have shown you that the strong electric field is in between the electric dipole, right? In that way, likewise. So what happened? Let's see. Equipotential, we can prove it mathematically. Equipotential surfaces indicates regions of strong or weak electric field. Wherever there is a strong electric field, what happened? There will be a crowded equipotential surface. Okay, will be there. So let's see. If dV is the potential difference between any two equipotential surface, then using the formula of that relation between your electric field intensity and a potential gradient, okay, dV is what? This is a difference in potential between any two equipotential surface. Okay, any 2 points of different equipotential surface, I mean not on the same equipotential surface. Okay, for 2 equipotential surfaces, right? Then using that relation between electric field intensity and what? Negative of potential gradient, then your dr can be expressed as what? Dv by E. So dr will be equal to minus dv by E. This implies that dr will be equal to what? This dv. Got it? If it is going to give you a constant quantity, that means difference in potential will remain same, because it is of 2 potentials. Okay, so let me draw it and let me explain you. Okay, why can't it pull down? Yes, it's coming. Yes, suppose if you are taking 2 equipotential surface like this, got it, and the distance between these 2 equipotential surface, let's take it that this is equipotential surface 1 and this as equipotential surface 2. Okay, and at some region somewhere here, the distance between these 2 equipotential surface is more. The distance here is more. Somewhere here the distance is less. Less in distance means what? Field is stronger somewhere here than somewhere here. Got it? So at a point A, let's take this as A, and at some region somewhere here at B, B is what? Weaker in electric field than somewhere here at position or region A. How we can say? Now, irrespective of this distance, the potential difference of these 2 points, whether distance is far or distance is close, it is immaterial. Why? Because this is of the same potential, this is also of the same potential. Potential, say let's take it that this is having electric potential, I mean for this equipotential surface, let's take it that is of say 5 volt, and the equipotential for this, I mean the potential onto this second surface, let's take it that the potential for this second equipotential surface, let's take it as 10 volt. So the difference of potentials between these two equipotential surface at this region will be also 10 minus 5, that will be also what, 5 volt, am I right, 5 volt. And at this point also the difference in potential will be 10 minus 5, this will be also 5 volt, am I right. So this 5 volt difference in potential between these two what equipotential surface at every region will be remaining constant, same 5 volt 5 volt. That is the meaning, that is what I mean here as constant. Got it? So let's forget about that sign. Got it? The direction. Got it? Let's take it only in magnitude. So that will be a constant quantity. Got it? So you can express this dV is constant, difference in potential. Okay, that will remain constant. So your dr can be expressed as constant divided by E. Got it? Constant divided by E. So what happened? Your dr is inversely proportional to electric field E. We can write it in that way, right? So your dr is nothing but the distance between the two equipotential surface. So distance and this electric field E are inversely proportional. So if dr is small, this will be large. If dr is large, then E will be small, inversely proportional. When one increases, the other decreases. When this decreases, this will be increasing. So what happens when this dr distance between the two equipotential surfaces is small, then electric field will be very, very large. So thus equipotential surfaces are close in the region of strong electric field. Got it? Yes. Number 4. No two equipotential surfaces intersect each other. Why we can't intersect? We cannot have any two equipotential surfaces intersect each other, because if we can intersect these two equipotential surfaces, then at the point of intersection it will surely have two values of electric potential. Okay, two electric potential, the values of two electric potential due to a given charge, okay, which is impossible for a given point charge or for a given charge or for a distribution of charge. At a particular point it should have a particular value of value of what, electric potential. But if you can have at a given point, if you can have two values of potential, that is what, meaningless, right? So which is also what, not possible. Got it? So these are the properties of what, electric potential and properties of equipotential surfaces. And in the next class we will try to do about that electric potential energy of an electric dipole when placed inside a uniform electric field. Okay, that we will do in the next class. Got it? Yes, thank you.